Okay, so I want to get into sort of what biogeography actually is here. And there's sort of two components of the theory of island biogeography. Sorry, that's what I meant, not just biogeography, island biogeography. There's sort of two components or two patterns that feed into this theory. And so I want to break some of that down. And so we're going to look at two patterns of diversity in relation to islands. And just to sort of, I guess, set the stage here, you may be familiar with these guys, you may not. I usually don't get into the history too much of these things, but this is a big theory in biogeography, specifically island biogeography. So it's worth mentioning. And one of these guys is still alive. So it comes out of this collaboration between Robert MacArthur and Edward Wilson, also known as E.O. Wilson, very famous conservation biologist now. They created a pretty big revolution in the field of biogeography, is what that should probably say, by creating basically the field of island biogeography in the 1960s. So it was these two guys, um, and they were working on some stuff independently and together in conjunction with this almost perfect phenomena that happened in the Krakatoa Islands. And so basically this event plus MacArthur and Wilson's collaboration led to the entire field of island biogeography. And what happened here was that a volcanic eruption in the Krakatoa Islands in 1883 basically eliminated all of the life from several of these islands, just literally wiped it clean of life of any kind, basically just covering it in volcanic ash. But just 50 years later, extensive forests had developed on many of the larger islands. So basically, what happened was, you would never get, this is basically as close as you can get to laboratory settings possible. You can't really get any close, but is if you were going to design an experiment, you would basically, if you could do this, you can't, it's pretty unethical, but if you could, you would go to an island and do exactly this. You would just wipe all the life off of it and then see, okay, how does life show back up? What species show up? How does diversity, how much biodiversity is there in relation to these other island characteristics? So basically, it was this perfect setting for people to take observations. And it was in 1883, so that was, a while ago, but there were still plenty of zoologists and botanists and things around at the time. So it attracted a lot of attention and there was a lot of data that was collected at this time period. And what MacArthur and Wilson and some other people noticed over time is that there was this relationship that showed up, and this is the relationship between the number of species, which is usually referred to as species richness, and the area of the island. And so here we're looking at some of those West Indies islands, and we're looking at reptiles and amphibians, the diversity of those groups. So basically, what they noticed was that the species richness tended to increase as the area of the island increases. So here we have our area of these islands, these West Indies islands, and we're looking at the number of species or the species richness of the reptiles and amphibians. So there's lots of different species, and the number present on a given island tended to correspond to the area, and you can see this increasing trend. Larger islands had more species on them, basically, and smaller islands had fewer species on them. It's worth noting this is on a log scale, so just something to keep in mind. That's kind of the difference. This inset map or figure here is showing the same relationship here, but not on a log scale. Basically, just showing that once you get to a certain size of island, increases in the area don't necessarily correspond to increases in species richness as much. It's only for a certain range. But if you do it on a log scale, you can really clearly see that relationship. So that's what's going on here. They saw that the larger the island, the more species there were of these reptiles and amphibians. And larger studies have found very similar things. So they compared here, their isolated islands had fewer species per unit area than sample areas of similar sizes on continents. So basically, if you took if you took an island, you measured the area, and then you went to somewhere on a continent and measured that same area, um, the island would have fewer species on it than that same area would on a continent. And so basically, this relationship is stronger. It's probably hard to see with just your naked eye, but if you were to get the slope of the line, this slope would be steeper than this slope. And basically, so that relationship is stronger. The area and species richness relationship is stronger when you're dealing with islands than it is when you're dealing on the mainland. So something different was going on here than just, it's not just the area, it's the fact that it's an island. And so what exactly is going on here? It's actually super basic, super intuitive. That is, if you have a mainland and you have species that are constantly dispersing out from the mainland, either flying or swimming, or, if you're an organism that gets washed up along, on logs or debris of some kind, no matter how you're dispersing, because island 2 here has a greater area than island 1, your probability of running into it is greater than for island 1. And that's it. That's the whole thing, is that it's just larger, so you're more likely to find it or run into it and then colonize than a smaller island. And so that's basically the island area species relationship, is that larger islands, you have a higher probability of finding it or running into it, and so they get colonized more often than smaller islands do. It's super simple, actually. But there's another component here. So that's area was one pattern. The other pattern is what's called isolation. And what's meant by isolation is usually the distance from the mainland. So you can have there's two characteristics we're looking at here: the size of the island, but also the distance from the mainland. And in a number of organisms, there's been other patterns related to that distance. And so here for these bird species, they're seeing a decrease. I wouldn't worry too much about these x-axes. We can basically think of these as species richness, and so species richness tends to decrease as the distance from the mainland, in this case New Guinea, increases. And this is for birds, but we see this in mammals and in reptiles. Here we're looking at actually a temporal thing where the time in isolation corresponds to a decrease in species richness. Here, just isolation, species richness tends to decrease with the distance from the mainland. So what's going on here is that it's basically, a very similar thing. If you're an island, if you have two islands of the same size, the one that's closer is going to have a higher probability of things running into it than one that is farther away. And that's pretty much it. And so it comes again down to probabilities. And so if we were to look at if we were to make like some general models for these relationships, we could say that species richness tends to increase for island area, except if you get to a certain level of area, it doesn't seem to increase as much. And so you get this increasing, and then it just kind of levels off because it doesn't matter too much if you're an island here or here, it's not going to make much difference. But if you're an island here versus here, it makes a big difference. Um, and species richness tends to decrease with island isolation. And so if you're an island far away, you're going to have less species richness than if you're an island that's close. And I wouldn't worry too much really about the math stuff going on here. Basically what they're saying is similar to how what I just showed for island area. You get to there's threshold points. So if you're a really close island, then it doesn't really matter, because if you're here or if you're here, because most organisms have some minimal dispersal ability. So if you're really close, it's not going to make a big difference if you're, maybe a mile difference or something like, or less than that probably. If you're like 200 feet or something, difference, it's not going to make a huge difference. But once you get to a certain point, then you see a big steep decrease in species richness as isolation increases. But then once you get to a certain level, if you're so far away that it doesn't really matter, none of the organisms can get there, then it doesn't really matter. So it's not necessarily a linear relationship, it's actually nonlinear. Because if you're really close, then it doesn't seem to make much of a difference, and if you're really far away, it doesn't. But in the middle here, you get this really steep decrease. So that's sort of what's going on there. So if we were to sort of combine these things together, we can create a graphical model where we can say the number of species inhabiting an island represents an equilibrium between the opposing rates of colonization and extinction. So it looks tricky, but it's pretty simple. Here you have your species richness down here, and on our x-axis, and this is what's called the turnover rate, basically the rate at which new organisms are showing up and new species are showing up and replacing the ones that are dying and going extinct. And so basically, if you have you have immigration, new organisms showing up, and you have extinction, which is species going extinct. Where they cross is an equilibrium. So that's going to be where the species richness becomes stable. Basically, the amount of new species showing up is equal to the amount of existing species going extinct. So you get in an equilibrium. And basically, if you move away from this equilibrium, if immigration becomes greater, then basically you have these opposing forces that push it back towards stabilization. So that's basically what's going on there. If we want to now incorporate our island biogeography sort of dichotomy into this, it looks complicated, but it's actually really simple. Same thing here. The number of species on an island is going to be a function of the immigration to it and the extinction of the organisms there. Also, the size of the island, the size of the island, and how far it is from the mainland. So basically, if you're a close island and you're small, then this would be the relative species richness. There are not actual numbers here. This is just so you can visualize what's going on. If you're a near island but you're large, then you're going to have a larger number of species than the other one. If you're a faraway island but you're small, you're going to have the lowest amount of species here because you're both far away and small. If you're far away but large, then you're going to have a little bit more compared to this one. And so basically it's just showing you those relative ways that we can, or the relative ways that these things are going to interact and influence the amount of species on an island. Okay, so that's the crux of island biogeography theory. So I'm going to pause here, and there's a reading, and then in the next videos we'll look at some more evidence, and then eventually get into some of the weird things that can happen on islands. So keep working your way through the module, and I will see you in the next video.